Okay, in the last video we figured the work required, approximate work required to move a charge 1 centimeter at 40 degrees with the x-axis in the presence of an electric field that we calculated previously. Charge was 5 microcoulombs. Now let's ask the question, what's the potential difference between this point and this point, according to our approximate result, which was negative 0.19 joules to move that 5 microcoulomb charge. So how are you going to get that potential difference? Well, the answer is potential difference is the work per unit charge. So now let's be careful. It's actually equal and opposite to the work done by the field. So it's negative of the work done by the field divided by the charge on which the work was done. So this negative 0.19 joules is the work done by the field. Now the voltage is then the negative of that, which is 0.19 joules, divided by your 5 microcoulombs. 5 into 0.19 is 0.038, and then that's times 10 to the 6th. So I believe this is going to come out 3.8 times 10 to the 4th joules per coulomb, or 3.8 times 10 to the 4th volts. Now, does that make sense? That the potential difference, the potential should be greater at V than it is at A. Well, in order to move this charge, this positive charge from A to B, I'm going to have to do positive work because the field is trying to pull me, well, it's trying to pull me down here, but there's a component of the field along this line. We can just project the field up to that line. So there's a component of the field along that line. Then why not just sketch that approximate projection? So here's your right angle. So here's your field component parallel to the motion. It's going to be this times this. I've got to do work against the field, and when I have to do work to move something, I'm increasing its potential difference in the same way I'd increase the potential difference of a concrete block I lifted against gravity. More potential up here. Drop it, potential comes back in the form of kinetic. Move the charge from here to here, release it, comes back here with kinetic energy. Okay, so there's our 3.8 times 10 to the 4th volts. That's the potential difference between here and here. I'll also comment that the original problem, and I just realized it, didn't have 5 microcoulombs here, it had 5 coulombs. If I'd have moved 5 coulombs, then I'd have had negative 190,000 joules, okay? Negative 0.19 times 10 to the 6th. Negative 0.19 times a million, negative 190,000 joules of work to move 5 coulombs. And you might say, well, who's ever going to move that? Well, if you have a circuit, if somehow you have an electric field and you have current flowing, you could easily flow 5 coulombs through a lot of different types of configurations and require that kind of work. 190,000 joules is a good, substantial amount of work. Working at a pretty good rate, it'd take me about 3 minutes with my body to produce that much work. It's not an exorbitant amount of work. Okay, so we get that idea, and we connect this whole picture into voltage. Okay, I'm not going to go through the details of the calculation, but you might want to consider it, because it's another thing that could well arise. We've moved this charge from the origin to this point. Now we're closer to some of these charges and further away from others. When we move closer to a charge, our electrostatic potential relative to that charge changes. So if we take the change in electrostatic potential from here to here for this charge, and then for this charge, and then for this charge, this charge, and this charge, and add them up, we should get the change in the electrostatic potential from this point to this point, and that should be consistent with what we've calculated here. So we could depict that, just, here's this distance. Let's call this R1. We have this distance. Let's call this R2. This distance we'll call R3. This distance we'll call R4. And this distance, not surprisingly, we'll call R5. So we have these 5 distances. Now this is a motion of 1 centimeter at 40 degrees, so we can calculate the coordinates of this point, and we can calculate the coordinates of all these points, and then we can simply use the Pythagorean theorem to figure out the distance from this point to each of these points. There would be 5 of them to consider. And then at that point we could add up all the electrostatic potentials. Now remember, the electrostatic potential relative to infinity of a point is negative kq over r. Sorry, that's not negative kq over r, that's just kq over r. I was thinking about the integral of kq over r squared, which would give us a negative, and just wasn't thinking. So now, that would be the potential for one charge. So we could calculate these distances very easily. We could divide by the charge, the 2 microcoulomb charge, negative 2 microcoulomb charge at every point, and multiply by our constant k. Then we could sum them. So I'm just going to indicate that by, we could sum the kq over r's, and when we do that, we should find that the change in the electrostatic potential between here and here is equal to the 3 times 10 to the 4th volts. These calculations result in relatively small differences, big numbers with relatively small differences. It's really pretty much a little beyond what I want to do right now to try to estimate that in my head. So I went ahead and just did a quick spreadsheet calculation. And I came up with that equal to about 94,200 volts. Okay, when I summed up the calculation for all of these. When you sum up the calculation for the origin, for this point, yeah, let's see. Got to find a good color here. Don't have much of this left. Okay, for the origin for this point, it's easy to sum these because they're all the same. All these points are at 10 centimeters. When you do kq over r for q equal negative 2 microcoulombs, for each of these you're going to get 18,000 volts, and when you add them up you're going to get negative 90,000 volts. So at this point, the sum of the kq over r, might be a little hard to read that, is negative 90,000 volts. What's the difference? Okay, well, the difference is negative 4,200 volts. So that the delta V is negative 4,200 volts. That compares with what we got here, the 4,200 with the 3.8, but I've got a 10 to the 4th here where I've got just a 10 to the 3rd over there, so it doesn't work as well as I thought it would. Hang on a minute. Okay, I was careless with the spreadsheet. Every one of these should have an extra 0 in it. It's going to mess up the numbers a little bit, but now we have the right power. And okay, now the sign here is wrong. We have the negative negative 2 microcoulombs at every point, and that would give us an electric field. Well, I'm going to have to think back through that. We can reconcile that, but I'll have to do that in a subsequent correction. And you get the idea. And the whole concept here is that we do electric field times displacement vector. Multiply that by the charge, we get the force. Do the dot product of the force with delta S, we get the work. We divide the work by the charge that we're moving, and we get the voltage. Okay, and these are all ideas that you have to have kind of at your fingertips to think efficiently through these problems.